Welcome back. So we have been looking at how to solve recurrence relations using generating functions. So we have seen the definition of recurrence relations quite a number of times, and we also seen how the recurrence relations can be used or is used in various subjects. Particularly, we have seen how to use the recurrence relations for modeling problems. The goal is to find out how to solve these recurrence relations. Now, one of the techniques of solving it is first guess the solution and then prove by induction. And if you can guess it correctly, then proving it by induction is quite a straightforward thing. But the question is, how do we guess the solution? The technique one that we have looked at is that we unfold the definitions, and using this technique we have managed to guess the solution for a number of them. But then there are functions like this or recurrences like this for like the Fibonacci sequence, when the function is quite hard to guess, partly because this is what it is, and this is what we will be proving in this video. And sometimes the recurrence relation doesn't have a nice clean form. So we have seen that in that case we can upper bound and lower bound the function, and that would be sometimes good enough for us, at least asymptotically. So the idea is that in this case you can solve it for some n and then prove it using induction that the recurrence relation or the function is theta of some number, by doing two kind of inductions, induction for an upper bound and induction for a lower bound. So this is where what all we can do using the simple techniques, but still there are some recurrences for which you cannot do it. For example, this Fibonacci sequence. How do we guess this Fibonacci sequence? How do we even come up with the upper and lower bound when actually the value is like this? As I told you, this is what we will be proving, that Fn is actually this value today, not by induction, just by guessing, but we will actually come up with this formula. The way of doing it is what we have been looking at for the last 3 videos, is the generating functions. Now to quickly recap, if I have a sequence of A0, A1, A2 till A infinity, the generating function is defined as the polynomial or the power series, which is A0 plus A1x plus A2x square and so on, or namely the summation of an x power n. Now this is called the generating functions for this sequence A0, A1 till A infinity. The question is that, or the idea is that, if somehow we can compute the coefficient of x power n in this px, then we can get the formula for an. We have seen a couple of examples in the last 2 videos where we did it. Namely, we wrote the power series or the generating function, and then we used the recurrence relation to get write p of x as a function of x, and then we used or tried to understand the coefficient of x power n in that function by looking at its Taylor series. So for Taylor series is basically a way of getting expressing a function as an infinite polynomial, and we have here are some of the examples of Taylor series expansion that one might use. So in this particular video, let's go to the hardest problem of all, namely the Fibonacci numbers. So here is the recurrence relations. F0 equals to F1 equals to 1 and Fn equals to Fn minus 1 plus Fn minus 2. Now of course we start with writing the power series, which is P of x is F0 plus F1x plus F2x, so this is not F3 but this is F2x, and so on. So that is, it is summation of n fn x power n. And so p of x equals to, let's write down here, f0 plus f1x plus fn x power n for n greater than or equal to 2. I have not done anything till now. I have just written the everything after the second thing. But the fact is that for n greater than or equal to 2, I already have something like this. So I can write it down as px equals to f0 plus f1x plus, for n greater than or equal to 2, fn is written as fn minus 1 plus fn minus 2. Good. So let me expand it. So this is, of course, fn greater than or equal to 2, fn minus 1 times x power n plus fn minus 2 times x power n. Now, like we did for many things, let's look at this first term. So in fact, we can go back one step. Let's go look at this one. What is this one? Now, if I take away x, so this is x into summation n equals to greater than or equal to 2 f n minus 1 x power n minus 1. So what is this term? Note this is, here it is n equals to greater than or equal to 2 and n, here it is n minus 1. So that means I get, this is f1x plus f2x square plus f3x cube and so on. Which means this quantity is nothing but the px that we have minus f0, right? And f0 in our case is 1, of course, so, but this is px minus f0. Similarly here, if I take x squared common, I get summation n greater than or equal to 2 fn minus 2 x power n minus 2. And this is nothing but, you can see, f0 plus f1x plus f2x square and so on. So this is p of x, right? So again, by the same argument that we did in the last two videos, we first wrote down the power series and then we used the recurrence relation to split up the later terms, which helps us to get a formula like this. This is x times px minus x0 0 plus x square px. Now we can take the px's in one side and we get, of course, p of x minus x px minus x square px equals to f0 plus f1x minus f0x. Now since f0 equals to 1, so this is, and f1 equals to 1, is 1 plus x minus x, which is 1. And hence I get, so if I, that px equals to 1 by 1 minus x square. So without much hard work again, we have managed to write down the p of x as a function of x. All that is left to be done is now to understand or write down the Taylor series expansion of this function, and if we can do it, we understand the nth coefficient of that, right? So let me quickly see this one. Of course, this is f2, I made a mistake here, and we have got p of x equals to 1 minus x square. Question is that, how do you solve it? If you remember it last time, what it was 1 by 1 minus x into 1 minus 2x, and we wrote it as a sum of two reciprocals of two linear functions. But here we cannot do that. We have to do something similar, but we do it carefully. So the main way of doing it is to first factorize 1 minus x square. So note that 1 minus x square is nothing but 1 minus alpha x times 1 minus beta x. I can factorize it like we do, where alpha is equals to 1 plus square root 5 by 2, beta equals to 1 minus square root 5 by 2. And in that case, you can see that, so first of all, you can check that this can be done. This is something pretty easy thing to check. This is the usual factorization of quadratic formulas, like the formula that we use, minus b plus minus 4ac, b square minus 4ac by 2 I say, that formula. You can factorize 1 minus x square in this way, using this alpha and beta. And in that case, we can write 1 minus, or we can write this expression as this. This is something I'm not going to say how to do it. I leave it to you guys to check that this is true and you find out how one can apply to do it. It is a very simple technique to put it through. Right? So, we first factorize the denominator and then we write it down as this expression, which is, again, here note that this one is linear expression and this is also linear expression. It is 1 by a linear polynomial, or the polynomial of degree 1. Note that this is exactly what we wanted, because we know the Taylor series expansion of inverse of the linear functions. So, again, we have this term, and by Taylor series expansion, we can write down what is 1 minus alpha x and 1 minus beta x. So 1 minus alpha x is equals to 1 plus, so it is summation of alpha power n x power n and beta power n x power n, where alpha and beta are these two numbers, right? And thus we know, and we have therefore written the p of x as a polynomial where the coefficient of x power n from this thing is 1 by square root 5 alpha power n minus beta power n, and that is exactly equals to f of n. So, in other words, we get that the coefficient of x power n is fn, which is 1 minus, this is the alpha, right? This is, I just substitute the alpha and beta here, is 1 minus square root 5 by 2 power n minus 1 minus square root 5 by 2 power n by square root 5. So as you can see, almost like magic, one can come up with a compact form of the Fibonacci number, which is quite an impressive job. Again, the idea is write the generating functions, then try to use the recurrence relations to write the generating function as a function of x, and then write down Taylor series expansion of that using some tricks, and then by looking at the coefficient of x power n in fn, we have the number. Some of the recurrence relations that are still unsolved here are this one, t1 equals to 2, t2 equals to 3, and tn equals to tn minus 1 plus tn minus 2. I'll ask you guys to go and solve it for yourself. You do it, that's the end of an exercise. There's one more that is there, which is this number. fc of n plus 1 equals to summation I equals to 0 to n ci times cn minus 5. This is known as the Catalan number and it's quite a complicated one. But again, the solution is through generating functions. So we will be doing this, the solution for this thing in the next video. We also have this one called a deriving formula, d of n equals to n minus 1 into dn minus 1 times dn minus 2. Again, we will be talking about this formula also in the next set of videos.